Recording is rolling. Welcome to Wednesday. We're going to take today to do Atwood Lab, actually today and tomorrow. So to remind you guys what's going on this week in physics, here's your guys' homework that's due in a couple of days. Whatever, these problems on Monday and these problems on Tuesday. So I bet most of you guys actually have this done already if you were just following along. If you want to do the bonus homework, then that's those problems there. You can turn that in too for extra points if you want them. So today, do you guys see click to the right side of your desk is the page that looks like this? This is going to be a two-part Atwood Lab. So the left side of this page, there's the classic double elevator setup. You guys will have time to do this today. And then on the right side, there's a modified version of that includes a horizontal component of tension. So that one we'll save for tomorrow. But I want to take you guys through the free body diagrams for those first to you guys into physics. Get a physics formula. So can you guys draw the free body diagrams on each of the masses for each of the setups? The classic double elevator and then the modified version that has the horizontal motion. Right. So I'm just going to copy those diagrams, but blow them up, split this paper in half to left and right side. And so there's the classic double elevator. Looks something like this. Got string. Maybe there's a big old mass you start up here. I'll call that mass A. And maybe a smaller mass down here. I'll call it mass B. Now, what are the forces on each one of those? We'll start with this and worry about the other one later. Okay, so I know that each of these blocks has a weight, like Earth's gravity trying to pull it down. The bigger one, well, that implies more mass, more weight. So it's got a downward force equal to mg. But I'll throw a little subscript A on that mass, say like mass ag. Okay, so that's the weight of block A. Now block B has also that force, but well, it's going to be less. It's going to be a smaller force, so mvg, because it has a smaller mass. So less gravity pull. Okay. And you guys might remember too that those two forces right there are the only two external forces on the system that are driving it to accelerate. It looks like overall this is going to accelerate clockwise, right? Mass A is going to accelerate down, mass B is going to accelerate up. At the same rate, though, right? Same magnitude acceleration. They're tied together by a string. Now, there are some other forces on each block. There's one more force on each block, which is the tension force pulling up. But I was telling you guys, too, that this force, the tension force, is internal to the system. And what that means is it's just holding the blocks together. It's holding the whole system together, labeled as T for tension. But it's not a net, it's not one of the external forces that's causing a net force driving the system to move. So it wouldn't be included in Newton's second law of motion. So last couple of days when I've been solving problems like this and showing you guys what is the acceleration of the system, the forces that are pushing us around causing it to accelerate are only the weights of the blocks. The tension is just internal, just holding everything together. And notice how I drew the tension as what I've been calling the Goldilocks force. Notice that it's larger in magnitude than the weight of the small weight, but it's also smaller than the weight of the large weight. You guys see that? See, it's like the middle force in magnitude. And see why that would make sense. Because if this whole system is going to accelerate clockwise, that means mass A is going to accelerate down, means the net force must be down. Oh, so the tension must be less than the weight of the large weight. And then vice versa for mass B, well, this one must be accelerating upward, which means the net force must be upward, which means that tension is more than that weight. Guess that? So that is the free body diagram, FBD. Well, actually, two free body diagrams, one for each lab masses. What would the modified one look like? And when I have you guys do this tomorrow, you guys see I actually drew a little Hot Wheels car underneath this one. The idea of that is to pretty much get rid of the friction. So there's like no friction underneath this one, or negligible friction. Okay? Right, so what does that pair of free body diagrams look like? Well, there was a horizontal table. There was a cliff drop off. There's a floor down here. Patch this in just to make it really obvious that this is all some physical material there. There's this pulley off to the right side. When you guys get the pulleys, there are these red pulleys that spin really well. So low mass, low friction. So low mass, low friction pulley. You can throw a weight down here, call this mass A, and throw another one up here. I'll call this mass B, but that would also include the Hot Wheels car that it would be attached to. It includes that mass also. Right. These are all connected by a string. So string, zero, string, like that. Okay, tied together. Oh, what are the forces? So I know that this mass A has a weight. So I'll call it mg. But again, I'll throw a little subscript A on that mass to say that weight specifically. Okay. Now mass B, I know also has a weight. Notice how I drew mass B as larger, and there's a practical reason for that. Would you guys agree that the larger the mass B is, it's going to slow down the motion of the system, which would actually make it easier to time with the stopwatch. There are a bunch of little tidbits like this that you guys will realize that once you guys get your hands on the materials and the stopwatch and whatnot, which is that, in the case of the one I'm doing now, if mass A is relatively small and mass B is relatively large, it's going to accelerate slowly, which is easier to time. Right? So as this mass is falling, and you can think of a similar story on the double elevator outlet. We talked about this the last couple of days, the extreme boundary conditions. So if these two masses are very close to each other, again, it's going to accelerate very slowly. That's a lot easier to time with a stopwatch. Versus if you were to throw almost all the mass on one side, almost all the weight on one side, that would accelerate pretty close to free fall, and that would be very difficult to time accurately. So finish off these free body diagrams. I'm going to draw a big old weight for this mass B. This mass B has a big old weight, I would be saying, according to my picture. But you know what? That weight actually is not driving the system to move because, well, this is on a horizontal plane. There's also the normal force holding this up. So there's a normal force straight up called the normal force, which is equivalent to that weight, which means that this guy and this guy cancel out. So the net force vertically is 0. Now there is a net force on this spot, but it's just represented by the tension force in the string. Now I'm going to make that a kind of a small tension force. Why would that be kind of small? Because this one string, one tension, the same tension is acting up on this other block. Similar to the double elevator outlet. Remember, the tension was the same as the string? I mean, if it's a massless frictionless pulley, that string can only have one tension in it. Same story here. And to make this completely consistent, see how mass A has a net force down? Its weight is more than the tension pulling it up. That means that the net force is down, so it will accelerate down, which is going to be true regardless of the weights that you pick. I mean, you can pick extreme boundary conditions. Like you can make mass A almost all the way, mass B like a paperclip, in which case it would accelerate pretty much free fall, close to free fall. Or you can switch the other way. You can have mass A be basically a paperclip, just like a couple of grams, and mass B is like a big old mass. It would accelerate extremely slowly, but some value. And so the weight of mass A being more than tension is always going to be true. There you go. That's the free body diagram, or actually 2 free body diagrams for that modified type outlet. You guys good so far? All right, so hopefully you guys are back in a physics mindset now. You guys remember, we've been solving stuff like this for quite a while now, last few days. All right, let's take a look at the lab page that you guys just picked up. You guys all found this page, right? Click to the right side of your desk. All right, so like I said, this is lab's in 2 parts. We'll do the left side today and the right side tomorrow. So let's look at this double elevator outlet. Now, here's the picture setup. Now, this is a very cartoony type setup. One of the practical tidbits is that if you use a very long string, more close to this picture that I actually drew in ink right here, it's going to be easier to time. Say if the string is at least a meter long, or you want it to be at least a meter long. I'll throw that, and you guys will see as you're working with these materials why that would be the case. Right, so you have a pretty long string, at least a meter long. How are you reading this table, and what's the goal of this lab? What are you trying to figure out? I'll scroll all the way down to the bottom of this paper, so you guys know what we're trying to figure out. It says find a relationship among acceleration, free fall gravity, mass A and mass B, like some general expression. And I started it for you. It said acceleration is equal to. I wonder if you can find a general expression for how the system's going to accelerate. Of course, one block is accelerating down, one's up, but the magnitude would be the same for both because they're tied together. What's the acceleration of each block as a function of each of the masses and the gravity field? That's what you're trying to find. And helping you guys out a little bit too, because see how some of these columns have stars at the bottom? Right? One of the column, I'll go over what each of these columns are, but basically you can somehow multiply or divide the first 3 columns to somehow get the last column, which is going to represent acceleration, there's some general way to do it. So the answer to this lab is going to have no numbers in it. It's going to be all in terms of variables. How do you multiply or divide these columns to somehow get some numbers pretty close to the acceleration? Of course, there's two approaches to do this. The way we've been approaching it the last few days is just to do this all out on paper. Draw free body diagrams and do some calculations, like very textbook, Newton's second law of motion. But today and tomorrow, you guys are going to do the science version of this, which is to make observations and measurements and some calculations and see how do the numbers actually work out in the physical world. And hopefully it should be pretty close to what we've been doing. So what columns have we got? This column, G, 980. What's 980? Well, it's, centimeters per second squared. Hey, this would be perfect free fall, wouldn't it? Like 9.8 meters per second squared. But if you look real close, I did put centimeters and grams on this paper because that's more the order of magnitude of units that you guys will be working with next couple of days. Got to record the masses, the two masses, M1 and M2. I have those recorded. Then these next columns, I want you to take the difference and then also the sum of those masses. And then the difference, just take the absolute value. That's why I threw it on those absolute value bars. That's to say that, well, I don't care so much if this is accelerating clockwise or counterclockwise. I just care about the magnitude of that acceleration, ultimately. Okay? You guys will see why by the end that I want you to take the difference and then the sum. Or you might be able to reason out, or if you took really good notes the last couple of days, then it might make sense why this might match your notes. Okay. X in centimeters, well, that represents some displacement. And in this context, it's going to be, here, I'll go to this picture that I just drew up for you guys. X could be how far the masses would have moved, and you're going to time also how far that's going to be. So what I would do for X is I would start them off like this, heavy one up here, light one down here, and measure what is that distance in centimeters. And then what you're going to time is how much time does it take for those to switch locations? Where to go? How much time does that take? Now, they'll be speeding up as they're doing that if they start from rest, and that's going to involve some acceleration. So that's what we're trying to figure out. So do that 3 times, time those, how much time it takes to move that distance. Take an average, right? 3 times to take an average. That's a pretty common thing that we do in class. And then, if you know that the blocks started from rest, and you know how far they went and how much time they took, isn't that 3 pieces of kinematic information? Hey, that's what we've been doing up to, well, the last quiz that you guys took. You could calculate the acceleration from that information, couldn't you? You remember, here, and I helped you guys out a bit. I threw an equation. X equals 1/2 AT squared. Hey, that's that college equation. How deep is the mine shaft? It's about 125 meters. Is that exactly the equation that Paul Hewitt was navigating to figure that out? That's not, but you can rearrange it and solve it in terms of acceleration. Acceleration ends up being this expression here. So I'm helping you guys out a bit. You can solve for the acceleration based on how far the blocks moved and how much time that took. Okay? So you can calculate that. And I bet you guys can figure out too that this acceleration will have certain boundary conditions. And what's the smallest value that this cell could be? 0 centimeters per second squared. And that's if the 2 masses were identical, it would work out that way. What's the largest value that this could be? How about 980 centimeters per second squared? That's if you were to stack all the way to one side, and also if you timed it exactly accurately, which would be kind of difficult to do for that particular setup. But you guys see that? All right, so throughout the lab, you're going to swap out, try different masses. As you try these, you'll find some setups are easier than others. Have you guys figure out how that works? Time, how long it takes to move some distance. You can calculate the acceleration, and then you'll have a bunch of values. So remember those start columns that I mentioned before? So one of the start columns is the pure free fall rate. One of the start columns is the sum of the masses. One is the difference of the masses, difference in sum. Okay. And then the last start column is the calculated acceleration value, based on the distance and time. Okay. And there's some way that you should be able to multiply or divide the first 3 columns so that it should land you pretty consistently numbers that are pretty close to that calculated acceleration. And once you figure that out, then you will have unlocked the answer to at least this half of the lab, again, in terms of variables. Okay? That makes sense. Okay. You guys got any questions so far? Questions so far? Okay. I'll throw one more hint at you guys before you guys take off to the lab. You guys see this setup? One thing that you guys will find out pretty quickly is that if the masses are pretty close to each other, that it'll accelerate slowly, which is a lot easier to time. And one way to do this is you could actually attach like the same weight, like 200 grams, and then attach an additional very tiny weight, so just to nudge up one a little bit. So that's one tidbit that could be helpful. All right, I will walk around, help you guys out, and we're doing this live today and tomorrow.